So I don't know, for some reason, like it won't have that there. And
Yeah, but I have the PDF, and I think it's easier, but okay.
So we've got to let it now. I don't want to like hold things up too much. Okay, we're like, cool. So you've got your cameras here, so the mic's there for the live stream. So yeah, obviously don't like walk too far away, basically, and just watch the videos and stuff.
Yeah, okay, that's good.
Okay, so we'll stick this mic on again, and that's just spare.
So I'm
No, I was good this one.
oh yeah, okay, that's great.
We all good? Hello. Okay, so we have Alessandra now from TU Delft. So Alessandra helped so much in the first and second PocketQube workshops. She put in one hell of a shift to try and get some momentum into the community, and yeah, really appreciate all the efforts over the years to try and get things going, especially at TU Delft. We're going to hear a little bit of an update on the program and some of the stuff they've been working on over the last sort of year and a half. So without further ado, Alessandra.
Yeah, thanks, Tom. It's a real pleasure to be here, and it's for this time I'm enjoying just participating, while the previous times I was heavily organizing it. But so yesterday you heard about already the Delphi PQ subsystems. Chef Kata gave a very nice presentation about it. Today I'm going to give a higher level presentation about where we are at TU Delft. I will start first with a bit of a background. Most of you went to TU Delft last year, so you might have had the chance to walk around the campus. TU Delft is a quite old university. It was founded in 1842 by the King William II, and it was turned into technical university in 1986, which means that we have only technical faculties. We have a quite large number of students. The latest number is 23,461. With an amazing amount of PhD students of 2,799, and we have lots of master and bachelor programs, a total of 32 master's programs. In total, we have 3,063 academic staffs, and we produce many publications every year. Across the campus, we have a lot of expertise space. So it's not only our faculty, the aerospace engineering faculty, but we do cover many aspects of the space research. And you can see on the left hand side the faculties and different areas. And I'm afraid you cannot see very well, but just to give you an idea of different topics we cover. And in order to facilitate the communication across faculties, we created an institute, the Delft Space Institute, which has as mandate to gather together people from TU Delft that work on research for space in order to maximize the impact in space research. And we have 3 teams. This again, I'm afraid you cannot see, but the 3 focal areas are on this side. We have space distributed systems, which is something that is interesting for PocketQubes, and then we have sensing from space, so measuring physical information from space, and the third one is less related to PocketQubes, is robotics. Okay, so coming to my faculty, aerospace engineering, we cover the most important areas of aerospace engineering, and it is one of the largest faculty in Western Europe, and we also score very well in the university rankings, so we are basically every year in the top 20 university over the world, which is very impressive being a public university. So our fee is rather low compared to private universities. So we are very, very popular, and we get many, many students every year. So in total, including bachelor and master students, we have 2,700 students spread over different departments, and an amount of PhD students about 170. For space engineering. We have 130 master students. And I belong to the chair Space System Engineering. We are 13 staff members, so researchers, assistant professors, lecturers, and we have 11 PhD students. Our key projects are small satellites, as many of you know already. So we developed Delphi C3, Delphi Next, and now we're busy with Delphi PQ. We cover many areas of space research, the engineering of nano and microsatellites, distributed space systems, navigation, propulsion, in general system engineering, and miniaturized instrumentation. And personally, I am an expert in radiation hardness assurance, so we do cover also the aspect of reliability related to space radiation. From the aerospace engineering faculty, and in particular from the space department, some spin-off companies were generated, and some of them became in the meantime very successful, like ISIS, that I guess all of you know, but also SNT, Norway, T-, and Hyperion Technologies. They are now very well established in the space community. In-house, we have facilities. First of all, we have a clean room that Chef Cat is managing, is responsible for our clean room, which is used for integration of satellites. Nowadays is not the case, but we still use it as a workshop for developing our space systems. What is also very interesting is that we own our own ground station. So we have on top of a very high building, the electrical engineering building, we call it EVI. So you can see it on a picture, this iconic building. Now it's a sort of a monument for Delft. It's one of the highest, 90 meters high. And some years ago, there was the idea of having antennas because it's an ideal location. So from time to time, we have visits to the roof, as you can see in the picture, and we have multiple antennas, huge HV, VHV for amateur up and down link, and S-band downlink. This ground station is managed together with the ISIS, so they do use it every day to track their CubeSats. And we also plan to use it for Delphi PQ. So in general, our activities fall under Delphi Space Program, which was established some years ago with clear objectives. And these objectives are hands-on education, so it is very important that we develop things that can be used in our education programs, but also research and development for miniaturized systems. We also aim at demonstrating the technology that we develop and provides a new space application in an end-to-end approach of very small satellites. So Delphi program produced already 2 successful CubeSats, and we were pioneers in this because we were the first one to launch a CubeSat in the Netherlands, which is a small country, but still for us is a very reason for being very, very proud. Especially Delphi C3 we are still very proud of it because it's still functional. It was launched in 2008 and is still going on, so it was much beyond the expectations. It was launched in a sun-synchronous orbit at 635 kilometers, and it's a 3-unit CubeSat with a mass of 2.4 kilograms. And as I said, it's still operational. Then we developed a few years later, 5 years later in 2013, Delphi Next was launched, which was an iteration, the next step with respect to Delphi C3. And it was launched in a LEO orbit and an altitude between 600 and 780 kilometers. This is also a true 3-unit CubeSat with a mass of 3.5 kilograms. Unfortunately, Delphi Next didn't have the same luck as Delphi C3, and it was claimed unoperational after 2 months of launch, but it succeeded to achieve the goals that we set for the satellite. So we realized that developing CubeSat can take quite a long time, so it was 5 years between the first two. And then we were thinking about something innovative, something new, and especially something that could lower the development time. So we decided to go for PocketQubes, as you know already. And the reasons why we decided to go for PocketQubes are many, but the main ones are the fact that it's a low tier out, so there is opportunities for research because we are a university, so we are looking for research. We are less interested in a business model, but we really want to investigate new stuff. It is an area which is still unpopulated, and we can see it's a very nice community, but still very small compared to the growing CubeSat community. So this is a nice position to be, to contribute to the development of the community. In general, PocketQubes offer very exciting challenges in terms of system engineering, which is our specialty. So we really enjoy trying to solve these challenges. And as I explained, one of our main research areas is miniaturization, and PocketQubes perfectly fit in the roadmap of miniaturization from CubeSat to PocketQubes and possibly eventually to satellite on chips. But what was really interesting was the idea of having a higher frequency of launches, which is unfortunately not yet the case. So this is where we are disappointed because we still have big problems, and we'll go back to this in the final consideration. Last but not least, it's the opportunity for education, because small satellites provides the opportunity to students to learn and to cover all the aspects of spacecraft engineering. So the team, you saw the faces, so the current members are unfortunately not many left, so it's only me, Chef Cat, and Stefano Speretta, our communication engineer, and we are supported by our professor, the chair of Space System Engineering, Professor Eberhard. And unfortunately, we had some losses in the meantime. So Jasper Baumeister, Silvana Radu, and Nikitas Fotenakis, they are no longer working for the PocketQube, and it's not clear whether we will have the resources to grow the team again. But in any case, even if we have a small team, we like to do things properly. And also because we teach space system engineering, we try to apply also to PocketQube, to the Delphi PQ, our best approach in system engineering. So the very famous and known V approach for system engineering, with the project definition phase, implementation, and especially important testing of the satellite. So what we have at the moment, you saw yesterday in the presentation of Chef Cat, we are developing, we are closer to the final delivery of the flight model of a 3P PocketQube. This size was decided because after a trade-off. So we decided that this is a nice size for allowing payloads, which are unfortunately not yet there, but in future we have tested and demonstrated that the bus, the core bus for implementing advanced payloads in the future. And we thought 1P was going to be too limited for our purposes. We have a functional EPS system, as you saw yesterday. We have solar panels, body-mounted solar panels, a battery board. We have an antenna, UHF and VHF. We have a radio, fully duplexed with over 2 separated bands. We have an onboard computer based on MSP for 3-2 microcontroller. We have an ADCS system with 3 magnetotorquers and 2 IMU in order to stabilize the detumbling of the satellite after launch for a speed up to 100 degrees per second. The launch, unfortunately, is TBD because we were very much ready to be launched together with the maiden flight of Vector R, and we got not too long ago the final fixed date, and a few weeks ago we heard that Vector is having lots of problems, economical problems, so our launch date is again not defined yet. So that's a very frustrating outcome, but together with Alba, with Tom, we are looking into options for launching Delphi PQ. So these are the subsystems, the pictures of the hardware you have seen also yesterday from Chef Kat's presentation. And Chef Kat also pointed out something that is very important to us because we are a university, and also because we have to fulfill the regulations in the Netherlands, which are pretty strict, also in terms of debris. And we don't want to have our Delphi PQ ending up in the 900,000 debris objects that are orbiting the Earth today. So we don't want to add any more piece of debris to that picture. And for this reason, we did, actually Jasper Baumeister did an analysis. I'm sorry because it's not very sharp. But this is an analysis of the lifetime. So on the y-axis, you can see the orbital lifetime. And the top line is 30 years. And we have a 25, which is the desired lifetime for we have to comply with. And this means with this calculation, depending on the size and the mass of the satellite, that we have to have an orbit which is lower than 630 kilometers in order to re-enter to decay in 25 years. But we are expecting that this limit of 25 years will decrease in the future. So we have to be ready in order to comply with stricter regulations that we think they will come soon. Now I would like to talk about a potential application of a swarm of PocketQubes, because this is my field, and I think it's also an ideal application for PocketQubes. So we have around the Earth, we have a very harsh radiation environment. We have the radiation belts generated by the magnetic field of the Earth. So we have the inner belt and the outer belt, and on top of that we have cosmic rays impinging our satellites every day. And of course this is a topic that is much covered by very professional research institutions, especially in the US. So there are dedicated satellites just monitoring the space weather, the environment of the Earth. But what is characteristic of radiation environment is that there is a high variability across space and time. So you really have an advantage having a constellation of satellites mapping as accurately as possible the radiation environment with a high number of small satellites. This is ideal. And of course, we cannot compete with the big satellites having on board scientific instrumentation, but there are a couple of ideas which are simple to implement, and they are possible to be implemented also on a PocketQube. It is enough to have just a memory and counting the rate of the upset in the memory to have an understanding of what's going on. And on top of that, another advantage of a constellation of the very same satellite is that you don't have to compare apples and pears. You have the very same satellite, you have the very same components, and you are sure that you are testing only the radiation environment. So this is this is for us a very interesting application, and we hope that in the second iteration of our Delphi PQ, we will have on board at least one or two of this kind of payloads for single event effects measurements. Now I would like to conclude with a risk analysis that we ran because we were having some problems, as I said, especially in the manpower part of the management of the project. And I think it's interesting to share what we learned from what we have been doing so far. So the risk analysis was based on different categories for risks, and is following a classical approach of likelihood and consequences type of plot, as you can see on the right-hand side. And we have categories for schedule, personnel, spacecraft, cost, and launch categories. Again, the picture is not very sharp on this screen. It was on my laptop, but you can see in the red area mainly personnel, so manpower, and schedule risks are the most critical ones. So we believe that having enough people committed to the project can solve all the technical problems, but still this is an issue that we are facing at the moment. And the reasons are summarized in this last slide. First of all, access to space remains problematic. So this is the third workshop that we are having, but still not much improvements in terms of flying PocketQubes. And this is really a source of frustration for people working on the project. Development time is too long because, yeah, the advantage of PocketQubes is really having a high frequency of launch, but again, this is not happening. Something that also we found out is that software can be very problematic in the development of a PocketQube, because you have to have a software ready in order to test properly the subsystems, and the software can, actually shows all the problems in the hardware. So it's important to have, this is what we learned. We postponed the software development after some hardware development, but we find important to start as soon as possible with software development. Another issue we have is the turnover of the team members. We had many losses. I showed you only the last ones, but previously we had 3 system engineers in our team, and they left for one reason or another. And probably this is due to the fact that the launch is so unsecure. And having a launch date, a deadline, helps keeping the people committed to the project because they want to see the end of the project. What we were not very good at is student involvement. Again, this is related to the long time which is taking to develop the satellites. So students typically stay with us 6 months. They want to move on, and they don't find a thesis on a PocketQube interesting enough because they are not guaranteed that they will see the end of the project. Another big problem for us is that it's difficult to get external funding. We are very healthy in terms of internal fundings, but our management is complaining all the time that we need to be sustainable. So we cannot live upon a first money stream given by the government. We need to find sponsorships, but it's still difficult. And the last point is lack of application. So when you want to sell the idea of a PocketQube, people ask you, okay, but what's for? What is the application? And I think the radiation monitoring is a nice application, but it's also something that is done already. So it's not that innovative enough to convince people to support PocketQube's development. So this concludes my presentation. So thank you for the attention, and I'm happy to take any question. Thank you.
So we have time for one quick question. So does anybody have a question for Alessandro? Over here. Please shout out with us. Shout. Can you shout the question? So the question is, do you think you'd have more applications by working with industry? Is that right?
Yeah, definitely, definitely. But it's again a little bit of a problem, chicken and egg. The industry sometimes they don't have themselves an application, so they ask us to find them one for them, and it's. But for sure, working with the private companies might help in achieving, shorter development time.
Oh, sorry. We've got Julie Trail now from Minicubes. So Julie's came all the way from America. This is another American talk. We've got a lot of American talks this year.
Might have some problems. Did it come through okay?
It's the thing,
I think it's because you did the windscreen thing.
Yeah.
How did you get
let me try it with my iPad.
So we need to get that. And then we plug that into that.
All right, let's see if we can make this
Just got
work.
a really cool 1P from this. It's with 3D printing, and I'm sure you can tell you a lot about some of the challenges and some of the cool stuff we've been doing on that machine. And also he has some of the takes around the opportunities. So if you want to do a satellite, then feel free to do that. So
Yeah, so I have to like near.
so Apple can talk for getting the resolution sorted. Got the floor for 25 minutes.
Okay, 25 minutes and counting. All right, good morning, everyone. Thank you, Tom, for the introduction. Before I start, I want to give a couple of thank yous out. The first one's going to be to my wife, who's let me come here without her. Okay, so that's a big deal. I also want to thank Julian over here, and Tom right there, because they've inspired me to keep going even when I was out of my depth. Find some people who inspire you, follow them, and then you'll keep going. Okay, so overcoming technical challenges when you don't know what you're doing. Oh, and by the way, hi to everybody on the live stream. I am not a rocket scientist. I pretend to be one. Okay. So here's my idea, the plan. We're going to design and build a satellite. We're going to launch it, fame and fortune away, right? It didn't work out that way. Okay, this is the reality. Integrating hardware and software is really hard. Really hard. First lesson you learn is know what you don't know. And if you've never done this, there's a lot you don't know. It's going to cost a lot more than you think. And it always takes longer than you plan. Okay? If I had only known. Have a support team. I'm a one-man shop. I rely on the PocketQube for assistance. Other than that, there's nobody in Pennsylvania doing this. Okay, there are only like 5 or 6 people in all of the United States doing this. So right now, this room tops everything we're doing. Congratulations, everybody. Read a lot. This book, Spacecraft Systems Engineering, sits by my nightstand. Yeah, if you want to sleep, it's a good book. But read it, learn it, understand it. This will help you get further along in your satellite development than anything else. It's just great. And be ready for things to go wrong. Keep fighting. You will win eventually. Okay. Now, when I say I work alone, I do have a few collaborators. Okay. Alba Orbitals first, Teachers in Space. These are some folks who I've worked with for the last 6 years, working on CubeSats, so we've been able to adapt some of what I've done there into the PocketQube. Have an electronics supplier, and then W.G. Malden is my former boss. I'm going to take a moment here and sidestep and digress. How many of you have a glass of water on your table? Everybody, that's just tap water, right? Do you know where it was 4 days ago? Anybody want to take a guess? It was somebody else's tap water. The entire systems that we use to process water are in dire need of monitoring, which is what my ultimate goal is. How do we monitor water? This is a test to see whether or not we can start doing things in space to monitor our water systems better. Okay? So that's what we're building. This is my shop. It is 3 meters by 3.5 meters. That's it. And there is a clean room in it, so that takes up a lot of space. But this is what we're building. We have a 3D printed plastic satellite. It's WinForm XT 2.0. It's made out of carbon fiber and plastic. $350 to have it manufactured, which for an aerospace grade NASA certified material, that's pretty cheap. The CPU and the logic board. Now I have samples, they're on my seat there. I'll be glad to show anybody these things. But I started with the Intel Edison. Anybody familiar with that processor? All right. It's a great little processor, right up until the point they discontinued it. Okay. I was in the middle of my software design when they discontinued the processor. I blew the processor out. Okay, ESD folks, it's a good thing. And I ended up not being able to get any more. So I switched to the NanoPi. The NanoPi was working great, except it was also discontinued and replaced with the NanoPi Air. This is supposedly a long-term system, so I should have it for a while, right? End of life in 2025. While I'm hopeful, I don't think it'll make it that long. The industry's moving too fast. Okay? But it's a great processor. I mean, look at those specs. Okay? Decided to put a few sensors on board: temperature, pressure, accelerometer, gyroscope, magnetometer, the usual stuff. The dosimeter I had to scrap. There is not a dosimeter yet in the form factor that works at the temperatures in space. They do make one that small, and I'm very interested in it, but I'm not interested in risking my PocketQube on something I really don't need to be measuring. All the other information is important. As a matter of fact, we have 3 temperature sensors on board, just so we're covering temperature across the spectrum. But this is an Earth observation satellite. That's its objective. Can we do this? So we got an off-the-shelf 5 megapixel camera. When you work out the math, it's about 250 meters per pixel. Not great, but it's a PocketQube. In 50 millimeters, we're taking pictures of the Earth. That's the idea. Okay? Expensive, but reliable. These things are all over the internet. And when I say cheap, cheap. $20. Okay, so between my processor and my camera, I'm still under $100. Communications, well, 450 megahertz radio, uses less than a lot of power, and we are licensed by the FCC. Power system, this is another fun one, okay? I started with some Trisol X that were obsoleted. Are you catching a theme here? I've now moved on to a mono solar cell and using compressed light poly batteries. By the way, don't look for the monocell solar cells anymore because they were discontinued too. The compressed light poly batteries, they're essentially a bag battery like you're used to seeing, but using the WinForm architecture, we keep the batteries in compression so vacuum is not an issue. Now, this I have in fact tested using an HTBE plastic on board the Perlin 2 glider when it was at 72,000 feet, which is essentially the equivalent of a Mars atmosphere. The batteries were exposed to that while in the compressed state, and they worked through better than 12 cycles of flight. Software, we're Ubuntu. It's Linux-based, real easy. LAMP stack, we put the whole thing on. Python for our GPIO, and then we have a Python to PHP bridge because I'm a PHP programmer. I wanted to prove that it would work, so I built one. It's connected to the internet. If you go to that address, you're talking to a mock-up of the satellite. using TCP/IP, just like we expect to be using. So write it down if you want to give it a shot. It's on all the time, unless I break it. So what can go wrong? Failure to reach orbit. Is anybody familiar with the comic XKCD? Okay. Up goer 5. Okay. If the flame end is pointing to space, you are going to have a bad day. Okay. I don't anticipate that. The rocket that we're on is the Electron. It's been successful. It's working. This is a good vehicle. I don't expect any issues. But it's still always a possibility. Launch is dangerous. Launch is risky. I know this firsthand. I've buried a couple of rockets in the desert in New Mexico. I haven't blown one up on the pad yet, but I used to do this rocket stuff. We could have a power failure or a communication issue. All right? And now with the tracking, because we have deployable solar panels, we're a little bit of a large target. Hopefully we can be tracked. But the reality is any one of these is a failure mode that can happen. Yeah. Paying for it all. I expected to spend about $50,000 to do this. Yeah, I'm currently at about $85,000 and climbing. When you don't know what you're doing, you end up paying. So, lesson learned. Get the education first. How many students in the room? How many students? Get your education first, then do this. Don't do it the other way around. It's cheaper. Okay. So, really, that's basically it. We're building a simple satellite. You guys know what PocketQubes are. We've been doing this for a while now. If you're new to the field, welcome. If you've been here, like some of the old timers here have been doing this, yeah, gray hair, I got it. So, I'm going to open the floor up to questions. That's it. That's all I wanted to present on. This is what we're doing. This is where we're at. And we hope to be flying here on this flight. Integration is in a couple of days, right? That's it. So questions. Which launch are we on? Tom, what is the official launch we're on? Tom? Where'd you go? Okay, the one that we're integrating out here on Monday, that's the flight I'm on. So it is an Electron flight. I just don't know if it's November or later. The name of the satellite is Discovery.
So you talked about getting education first. Where do you get that education? Because I'm studying aerospace engineering, and nothing of this, like PocketQube side, you learn.
That's a good question. Where do you learn this stuff when the universities aren't teaching it? Rule number 1, find a mentor. There is somebody out there who is doing this. They might be an insane, crazy old guy like me, but they're out there doing this. Learn from their mistakes. It'll save you a lot of time and money. Okay? Yes? How do you balance your time between learning and doing, basically? Now, imagine doing all of that while you have a full-time job. Okay. So, for my day job, I read about 3 hours a day, just to keep up with my industry. Okay. For the aerospace, I'm reading another 1.5 to 2 hours a day, and then I'm spending about 12 hours total a week in the studio building. Be ready for some long nights, is what I'm saying. If you're used to the long nights in university, you're all set. Okay? It's the same thing. It doesn't end. I wish I had better news for you. Like I said, I'm really trying to keep it under 20 minutes and get us on track so we can all go to lunch on time. Sound like a good idea? Any other questions? Ooh, quiet crowd. If you want it, I'll give it to you. I'll have it right down here at the table. So, and I do want to show you the processes. Before I conclude, I want to talk a little bit about the processes that I'm planning on using. You saw the one that I had. Okay, that is the H3 basically from the NanoPi. But they came out with this new thing called a TensorFlow. It's more for machine learning, but it runs Python really well. So I could do everything I'm doing with a full processor, including some basic database, in a cheaper, faster board. That's a win. Well, in the middle of starting to develop future product with it, they released an even smaller version. So my boards are 42 by 42, but the new board is 14 by 19 millimeters. Oh, and it includes Bluetooth. So I can talk back and forth to my processors wirelessly if necessary. Here's a new term for you, fly-by Wi-Fi. That's a reality that's coming, okay? But yeah, I have the processors there. You will love these things. They're microscopic, and they sip power, 0.6 milliwatts per megahertz. I can go to 96 megahertz on the processor. So think of it as an Arduino on steroids that doesn't use power. With a coin-sized battery, I can run for a year. How am I handling heat? So that's the beauty of the wind form. It already has a great thermodynamic set of properties. It can handle a curve better than 200 degrees Celsius from one corner to the other. So I'm not worried about that. The electronics are going to be my problem, and so heat dissipation within the satellite, I'm winging it. To be honest, I'm winging it. I'm not trying to do any of the math to govern that because it's just, there's a term that a database instructor, remember I told you to get mentors? A mentor of mine, he said, always ask the question, is the juice worth the squeeze? Okay. Do you really want to squeeze the lemon a little further to get just a little more juice out of it? If the answer is, no, it's not worth it, then don't do it. And for this type of an experiment, it's not worth it. Guaranteed, flight number 2, and there will be a second one. Regardless of the outcome here, there will be a second one. On that one, I'll probably do a more thorough analysis, because then I will have a better handle on it, and hopefully some funding. I'm sorry, I can barely hear you. Oh, how the use can be linked to water. Okay, one of the neat things about the visual spectrum is we can see, the visual spectrum is very limited for our eyes, but the cameras fortunately have infrared built into them. So if you use infrared in the visual spectrum, if you're looking at a waterway and there is a raw sewage event, there is a color and temperature change to the water that occurs instantly. You can measure that. It is significant enough that it can be measured. Not with this camera, okay? This is a prototype. But if you can get down to 25 meters per pixel, you can measure the change in color of the water in your waterways. So you can spot pollution or contaminants that enter the water at the time they do. Now it's a matter of frequency. You put enough satellites up, combine it with the existing data from Planet and other resources, and you can build a database that allows you to pinpoint all of this. Now imagine you're a municipality downstream from a pollution event. You could get an advanced warning by pager, by email, whatever methodology works for you, that lets you know there's a problem upstream so you can prepare your systems for it. That's the idea. Kind of crazy, isn't it? Any other questions? Thanks for relaying Stuart's question. Appreciate it. All right.
Go, well, good. Big round of applause for Joe. Laptops. You have a laptop? Is there a laptop charger now? I'll be talking today. Thank you very much, Joe. Really insightful. So the next talk is from someone who I've worked with for nearly 3 years now. Actually, maybe longer than that one enough. Me and Constantine go quite a long way back. to stream on Mondays actually.
Use the RPs.
Constantly runs our engineering team at Alba, so he's looking after all the engineers, making sure that we're all pulling in the right direction, that the schedules are met, and that the real goals are focusing on. He's going to do a talk on Unicorn 2, so some members of Unicorn 2 in the Alba stand. Constant's going to give you a sort of a technical update on where we are with things. I think in terms of like resources, we probably have more resources working on Unicorn 2 than a lot of teams, and we've been able to make great technical strides in the last couple of years. And we're very close now to shipping out the first flight articles for Star Space, so without taking away all the stuff, handled with Constantine. So use that mic and don't go too far from that's the live stream, and that's the cameras for live stream.
Right, okay. So, good morning everyone. My name is Konstantin. Tom did the introduction. So I'm going to talk about the Unicorn satellite. So what Alba Orbital has been doing, what is Alba Orbital, and how we moved from Unicorn 1 to Unicorn 2, which most of you have seen at the back. So first of all, a little bit on why miniaturization of the satellite and what the goal of Alba Orbital is. And I'm going to talk a little bit as well about the configuration of the current version of our satellite, and then mention some potential applications and collaborations we have. So first of all, the mission statement. I call it like that because I think it's funny. So our aim is to advance the PocketQube cause. The PocketQube cause, which all of you here know, and we want PocketQubes to matter. So I know you know that PocketQubes matter, but the cause is also to make presented to other people outside of the community and help grow the community, as well as developing the first, one of the first commercial versions of the satellite. So we all know this. Satellites have been miniaturized since at least the 90s, and it makes up for less junk in space, so it's good. And it also is less costly to launch, so you know this. And basically it opens up the possibility of having bigger constellations to do missions. So we make our model. What Alba Orbital does is, you have an idea for a satellite, you come to us, we can build you that satellite and we can make it fly. Or, as a lot of you here have, you have your own satellite and you want to fly it, so we fly it cheaply. So here you see our integration pods. So on the left, the 6P, and on the right, the model of the 96P pod, which is used to eject the satellites into space. So we currently have a flight model for the 6P pod, so where you can put up to 6 1P satellites or any other combination. And the end game for us is to actually have something like the box you see on the right, which is the 96P pod. It can take up to 96 small units, 1 unit, 1 piece, or any other combination. So you see Alba Orbital is pretty much 10 people and we're growing. We are currently planning for a 1 month, 1 satellite per month production rate. So that will be with our new facilities, which we are trying to build up, and will be ready for 2020 or 2021 if things get a bit late, which can happen. So the end game is shown here. We want to put the 96P pod onto the rocket and basically fly the constellations. So the first model that was developed from Alba Orbital was actually the Unicorn 1, which some of you may know. Those that do not know about the satellite, it's basically a 2P with a mass of a bit less than 500 grams. It has an orbit capability of on-orbit power of 1 watt, and it was the first model to be developed. It had a communication system at UHF and at S-band. The end game here was to actually do some Earth observation missions. We found out that we need to evolve this into something better, something bigger, and basically this is what we did by doing the Unicorn 2 satellite. So I'm going to assume that most of you have gone back at the expo area and seen it a little bit, so you know, you are familiar a bit with this picture. So it's pretty much, not pretty much, it's a 3P satellite which has active attitude stabilization, a guidance system. It has capabilities of generating up to 19 watts of power, that's peak power. We're currently using for the missions, we're planning up to 10 watts of power, so you have power to play with. It weighs about 650 grams, and you have 100 grams of payload available to play with, but we are actually optimizing that as well to have a bit more mass in there as well. What else? It has UART capabilities, UART protocols, it has a flash memory, it has an onboard computer, all the classic stuff you would expect from a PocketQube satellite, and it's obviously compatible. It's based on the PQ60 standard. So I'm going to, so the current version, can you see that? So it has basically, the current version we're using for our Earth observation mission has an optical payload, a UHF and S-band radios to communicate for uplink and downlink respectively. It has sun sensors, sorry, and basically, yeah, the optical lens, which is the camera. So I'm going to present here a schematic. That's better. So if you look at the small picture on the left, and you basically do a cross-sectional area, you see basically a more detailed version of the satellite. So the big black structure you see in the front is the optical lens. Behind it is our attitude control system, and you can see in the front a section of the S-band patch we're using for the downlink at a higher data rate, and the UHF antenna, which has been modified. If you notice closely, you will see that there is a green structure which is the base plate, and basically the base plate contains all the circuitry for the satellite. So basically the base plate is the brains of the satellite. It contains the onboard computer as well as the circuitry as well as the ADCS circuitry. And right beneath it, we actually put the batteries. So you have 2 lithium-ion batteries that are placed beneath the base plate, beneath the camera, and one on the front and at the back of the base plate. I'm sorry, I don't have a pointer, so I can't point precisely here. Basically, this is the configuration of the satellite. So the orange box is basically the base plate, and we have, as you can see, space to put up to 3 payloads. We have 2 sun sensors and 2 sets of, so 6 light resistors to help for the sun sensor for the active pointing for the sun. We also have obviously telemetry capabilities, and we have 3-axis ADCS. So we have 3 motors, 3 reaction wheels for it. And yeah, this is our basic standard configuration. So I'm going to talk a little bit more here about the reaction wheels, because that's one of the fortes of the satellite. Basically, we have a pointing accuracy of 5 degrees with a 2-axis sun sensor. As I mentioned, we have sun sensors in 2 axes. We also have 3 wheels and 3 reaction wheels and 3 magnet torquers, 1 per axis. So we have a full active stabilization system. The other thing I want to talk about is people talk about the satellite, but you also need to have a good Earth system configured to be able to talk to your satellite. So I'm going to talk a bit about the configuration we use for our ground station and what we have learned from this. So literally currently we're having an uplink and a downlink at 2 different frequencies, so we can go for full duplex communications. So I'm showing you here the ground station, which is at the roof of the Strathclyde University, which we had worked with, and this ground station is at has UHF and VHF capabilities, and our aim was to sort of refurbish the UHF part and add an S-band version to it. So what you need for the ground station, apart from the RF equipment, is motors and cables of high quality, motors to be able to properly, follow and turn your your radar, point your radar where you want. And actually, if you're planning on doing higher frequency if you're planning on doing higher frequency communications, let's say at S-band or above, you need to carefully choose your cables as well, because you need to minimize losses as much as possible. So that's quite essential, I'd say, but not only. So I had planned on discussing a little bit the ground station and what we are using for the UHF and S-band components, but I'm not gonna take too much time here. Basically, on the right side, on the red side is what we have on the satellite side. So you can see we literally only have our transceiver and an antenna. We don't have any other form of amplification or filtering. And on the left side, on the upper side, we have the configuration for the UHF ground station. So we have found this really good amplifier from Kuna Electronics, if I remember correctly, which is a bidirectional amplifier. It's a preamp, and at UHF, it will probably be sufficient. Obviously, you can go more complex and add LNAs and filters, but we already have that filtering part, at least on our transceiver side. This is the configuration for the ground station at S-band. So this particular one is meant to work between 2.2 and 2.5 gigahertz. Let me say straight away that on the left, you have on the upper side you have the ground station part, and on the right down side you have the satellite configuration. So again, for the S-band, we only have the transceiver and the antenna on the satellite part. So this can be a bit penalizing in terms of link margin for closing the link. So for that reason, you need to carefully choose a good antenna on the ground station side. So that would be a good dish and probably some extra amplification. I'd like to point out directly that there is a transmitting part on the ground station side for 2.4 gigahertz. Scratch that, because you don't want to use you don't want to uplink at 2.4 in rural, urban areas, because you're going to fry Wi-Fi's and people are not going to be happy about it. So that one, we just simply scratched. We have it there. I had it there for design purposes originally, and only design purposes. So with that being said, I'm going to give you some of the characteristics of the mission we're going to be flying soon. So we're going to fly with Unicorn 2A, a LEO mission at 385 kilometers with 97 degrees, sun-synchronous orbit anyway. We're going to use amateur frequencies for uplinking and downlinking, respectively 436 and 2.4 gigahertz. So up for UHF, down S-band. And this is going to be a tech demo for our Earth observation, payload. We have some of the characteristics of the link we're using. So our radios are currently capable of producing 1 watt of RF power. So we'll be using those one radio on the satellite, obviously, but we'll also be going to using the same radio on our ground station. We're using GFSK modulation, and there's a typo. In the S-band link, we're also using GFSK modulation. And as I said, the most important thing is to carefully choose the antennas and the cables, especially at higher frequencies. So for our ground station in S-band, we're using a big dish of 1.8 meters, that gives like 32 dBs of gain. We're aiming to have circularly polarized antennas on both ground stations. And what else can I say? Yeah, the radios are custom made. They are our own radios. For those of you that haven't seen them, we have them showcased in the other area. Whoa, that was too fast. So what we've learned from designing this ground station is, like I said, first of all, you need to choose your equipment carefully. So what the length of the cables are going to be, which cables, they need to have decent quality in terms of losses, especially at, like I said, at higher frequencies. Carefully plan the link budget. Sometimes it's straightforward, you just plug in some numbers, but there are out there some very good link budget templates that take into account some details that sometimes seem obvious, but they're not. For example, I'm thinking circular polarization versus linear polarization on each side. So our satellite has a linearly polarized antenna. We have a circularly polarized antenna on the ground, so you get a bit of losses there. It's not much, but if you start adding things like that, your link margin starts to get smaller and smaller, so you need to take that into account, things like that into account. Also need to plan in advance for vibing and thermal campaigns. Any test campaign you deem important, or your rocket provider deems important. And finally, choose the equipment well. So that does not mean choosing expensive equipment. It means choosing smart, to be able to find low-cost equipment that are optimized for your design. Finally, I'm going to talk a bit about potential applications. Most of you might be aware of these. One of the things we want to do is Earth observation. Earth observation is important to any country that has, for example, agricultural or maritime economy, which is many countries, not only in Europe, but around the world. So Earth observation is something that PocketQubes need to go into and prove that they can do it. It will open, we believe, access to the market it will make the PocketQube community grow. So yeah, it's a low-cost technology that we're building, and the idea is not to fly one of these, but many, so that we can do constellations. For example, for the Earth observation, if we do constellations, we will improve the temporal resolution of acquiring images a lot, almost to 1 per day or even more. Finally, we're also doing a bit of Internet of Things. So one of our clients has commissioned a couple of satellites from us to do a tech demo of an inter-satellite link. So again, this is something the PocketQube community we believe should do and should dig into it. And finally, we also have R&D collaborations when it comes to the PocketQube. So a couple of ideas here. We're talking about improving, for example, the resolution for our Earth observation mission. So we would look into deployable lenses, or even adding something like a small propulsion system. And I'm going to briefly talk here, give a bit of an example. So one of the R&D projects we're doing is with Heriot-Watt University, where we're trying to integrate antennas on the solar panel to be able to save space and potentially mass. So I'm just going to talk a bit briefly about this here. So basically, the Heriot-Watt group we're working with, of which Professor Podilchak is here today to do a presentation on that as well, has heritage on integrating such antennas. So we have here a picture of one of the solar panels of Unicorn 2. And the idea is to literally integrate some form of meshed grid for an antenna in the S-band range. To do that, on the right side, you can see that you can see the cross-section of the solar panel, of our solar panel, and basically the idea here is going to be to add a little bit of extra thickness in the form of an extra substrate, which will increase the mass, but in the end, if we are successful in this, we will remove the antennas we currently have, and we will save space, and actually the overall mass for this new antenna is going to be lower, or close, but lower, close to what the original antenna was. So we're doing also some R&D projects. We're very interested in also working with the academic community to be able to improve volume, mass, and efficiency of the Unicorn 2 with interesting projects that are projects that are also academically interesting. Finally, we're also, because this satellite was built with radio amateurs, so there's myself and there's been in Alba a couple of other radio amateurs. We're also very keen on working with ham radio amateurs, because let's face it, if you want your satellite to be tracked by a lot of people simultaneously, the ham community is where you go to as well. So for our first mission, we'll be organizing challenges where we're going to ask people to download some telemetry and track the satellite and hear it, and there will be some prizes. Don't ask me what the prizes are and the questions, because I do not know. So, yeah, that's it. Thank you very much for your attention. If you have any questions, I'll be glad to take them. They don't have a ceiling. Well, it's not. They do. It's just that they do. It's just that the photo I have is from a first model that was just for the showcasing. So I think in the model we have back there, I think you have the casing and the ceiling, but not the reaction wheels. Okay. Sorry? Which launch? So for this one, we had a launch, but with Vector, but we're gonna have to renegotiate that, to put it mildly. Yeah, that. Yeah,
we're also in Rocket Lab, so.
Yeah, forgot to say that. For our inter-satellite link, we'll be doing that with Rocket Labs. For the mission, for the client that commissioned the satellites from us for the inter-satellite link, that's with Rocket Lab. Our own mission was supposed to be with Vector, the Earth observation one. We'll figure it out. Okay.
Any more questions for Constantine? All good. Thanks very much. Give Constantine a round of applause. So if anyone wants to know anything more about Unicorn 2, the engineering team is down at the front here. So we've got pretty much everyone here. We had a lot of elements of marching. I think we lost 4 bodies in the last couple of days telling us, but our day here, I've been working on Unicorn 2 for a number of years now, and if you have any questions, come chat to them. So I'm sure they can help you guys out with some best plans in class. Thanks for that. So next up we have Oriole, and thankfully he showed up. It was looking sketchy for a while. So just standing for the podium.
Yeah.
So Oriole's from Spain, so he's pretty close to joining Cluster 2. Don't know exactly what stage it is, but we're hoping to have him in Cluster 3 pretty soon. It's like 1P or 2P now?
2P, yeah.
2P now, okay, cool. So Felix is a team leader, so he came to the TV Delta last year, and I think 8 people or something. So much of the Argentinians this year, they brought a lot from Europa University and AMSAT in Spain. So Oriole's going to get you up to date on the latest developments on the ESAT2 project, and it's interesting to have, there's not many 2Ps, to be honest. We started with 2P and Unicorn 1, and it's always nice to see more people doing the 2Ps. So yeah, so so we just get the light launched up and yeah.
Yeah, it's not responding, like, see when I load this thing up.
Well, hi everyone. While the presentation is being sorted out, I'll just introduce myself and talk about a little bit about the project. So, I'm Muriel. I'm from Spain. I'm from Barcelona, but I study in the Universidad Europea de Madrid, which is in Madrid. And together with AMSAT Spain, we're doing a collaboration to build a 2P. And okay. So yeah, it's called EASAT2, and the main. Well, I'll do a brief project description for you. So it's made by us, the undergraduates from aerospace engineering, mechanical engineering, and telecommunications engineering. And the undergrad students, we focus on doing the simulations, doing the structure, doing the orbital mechanics, the attitude control, and the people from AMSAT work, they are more focused on the telecommunications part, the electronics, etc. And we have, the main objective is to provide for a linear transponder so that radio amateurs can use a handheld device to talk from Spain to UK or very long distances, maybe even across the Atlantic Ocean. And there's already a CubeSat that does this, but no one has done it with PocketQube before. And we are sure that if it works nicely, we'll have a lot of traffic of radio amateurs with a $30 handheld device talking to each other all across Europe. Yeah, it's a 2P. We follow the PocketQube standard, and we use components off the shelf, of course. And the other objective is that from the university we wanted to test if you could use the difference in temperature that would naturally occur between the inside and the outside of the satellite to generate useful power. At first we thought about using a Stirling engine and just make it very small and just test if that could actually work, if it would generate power. But things got complicated. To launch some pressurized air is very, I wouldn't say dangerous, but the launchers see it that way. So we've kind of stopped on that. I'll explain more later. So yeah, the main objectives, of course, learn for us. We're students, we want to learn, we want to have someone to mentor us and like learn by doing. And also the space sector is very hard to get into, and so PocketQubes offer a great opportunity for us. And also radio amateurs, they are getting into the PocketQube sector, which is awesome. The other objective is to test that new power source. It's not really new, but on that scale it would be. And then, yeah, provide the linear transponder for radio amateurs. So I will talk about the main engineering challenges and just focus on how we solve them. First of all, the communications problem. So we wanted anyone with a $30 handheld device to be able, like a walkie-talkie, to talk through our satellite. And so to do that, we had to implement very long antennas. I'll show you in a minute. And those antennas would be non-directional, of course. And that plus a passive attitude control would mean that sometimes one of the antennas, because I'll show you, they are on the opposite sides. Maybe one antenna would be pointing onto the ground and the other to the space. So it was a bit of a challenge. The other, of course, the power budget. For the linear transponder to be used with voice, we needed power, and PocketQubes don't have a lot of circuits, so yeah. And then, yeah, the attitude control and the feasibility of a Stirling engine, which was one of the main challenges, of course. And then we wanted to reduce cost, and that meant designing everything by ourselves. And also, we wanted the lifespan, we wanted it limited by the decay of the orbit and not by the electronics.
And so we designed everything for long lifespan with failsafe, and well, I'll explain a bit more in a second. So for the long antennas, we couldn't just unfold them like many of you have done with the regular rulers and the magnetic unfolding rulers. And so we decided to use nitinol antennas. They are not really used in the sector, which once we got into testing them and everything, it was quite surprising. Nitinol extends by itself, well, it regains the original shape once you apply heat. And so that was our solution for the long antennas. Just like Fosasat, we would inclinate the magnet to have both antennas parallel to the ground over Europe and similar latitudes. And for the power budget, we would just pay more for better solar panels. That was the only solution, really. And also, to test the Stirling engine and generate power through the delta T, we needed to ensure that there was delta T. So we focused a lot of efforts on doing precise and good thermal design. And we also are implementing multi-layered insulation, which I don't think I've seen any other PocketQubes do that. And that would ensure that there was a very high delta T in between the inside and outside of the insulation. And for the long lifespan, especially AMSAT focused on fail-safe electronic design and avoiding integrated circuits. And yeah, just keep it as simple as possible within the objectives that we wanted to do. So yeah, we have 2 monopole antennas, and as you can see, the sizes, they are crazy. We're talking about 92 centimeters on one side and 48 centimeters on the other side, and the satellite is like 11.47 centimeters. So it's crazy. So we used nitinol, which, as I said, it's a shape memory. It has memory, and we tested on an anechoic chamber. But as some presentation said yesterday, maybe we should test it in an open field. And yeah, the ACS, just like everyone else, just put a magnet, put some hysteresis material, and you're good to go. But yeah, we've done some simulations with Snap. Well, you can see the size of the magnet, it's very small. Although we might increase it because the PocketQube launcher, they haven't set exactly what are the expected initial rates. Once we know them more precisely, we'll probably adapt the magnet for that initial spin rate. Yeah, we've done a lot of tests and learned in the way of doing the tests and building everything. For the onboard processor, we used an 8-bit 4 megahertz microcontroller, just the same as the $50 SAT. And yeah, the main objectives of the processor are sending telemetry, receiving telecommands, monitoring the battery, and as a new thing, we use software inside the satellite to avoid just putting an integrated radio and then increasing the lifespan. And also monitoring the noise level and deciding when there's a transmission. And well, yeah, you can see here the graph. Later, if you want, if anyone's interested, we can talk about it. For the power system, the power circuit, the main idea is just having very fail-safe design, avoiding as many integrated circuits as possible. And so, if any component fails, the whole circuit will keep going. Just like the same with the computer. If the computer breaks down, the satellite will keep working. The linear transponder will default to active all the time, and just keep going. For the solar panels, just what I said, just pay more and have better solar panels. We're talking about around 10K euros for the solar panels, but they're crazy. It's almost 1 watt per solar panel, which is it's exactly what we need in case everything else fails. The linear transponder could keep working just out of the solar cells and the linear transponder. And again, a lot of testing. You can see with the batteries, the stack, and everything. And for the linear transponder, it's interesting that we've done it, well, especially Eduardo, who's there, and other people from AMSAT, they've done it all like with single components. There's no integrated circuit, it's 1-by-1 component. And also there's duplicity. If any component was to fail because of a singular event or any, I don't know, heating up of the component, whatever, the whole thing will keep working. It will keep working. Maybe not the same, maybe not as good, but it will keep working. And that's one of the main philosophies of our satellite is it will have a slow degradation, but it will keep working until it falls down. Or that's what we want. For the steering engine, yeah. So we wanted to test you can actually use the difference in temperature in space. And so we decided for a free piston Stirling engine, which it would generate the minimum amount of vibration, and it didn't require any spinning. I don't know how they're called, but the gears. Sorry, yeah, the gears. No spinning gears, just a planar spring. And yeah, the design is currently on hold. As I said, the pressurized things in space, they think they are very dangerous, although they are 1 atmosphere, I don't know. Instead, we are considering using the thermoelectric effect, a Peltier model or something, to test that it can be done, but without pressurizing anything. And yeah, the thermal design was done with Cinda Patron. Very strong simulation, but very tedious to do. This one is without insulation, and the difference in temperatures across the different modes, which is in eclipse. So in eclipse, the two on the right, on the sun, so non-eclipse on the left, and then operating and non-operating. The difference in temperature was too big. We wanted the electronics to be very at a constant temperature, and we wanted just the outside of the insulation to have wild change in temperature, and then use that changing temperature. And this is one of the last simulations, which has the Stirling included, and the inside is very stable. You can see it here. The inside nodes will oscillate around from 9 degrees to 45 degrees Celsius. So very stable. The battery could work all the time if it works like that. And yeah, a lot of hours put into all the simulations. And finally, just the mechanical design. We've gone over several iterations. One of the first ones was use like what everyone else is doing, just having a box-like structure and mill-that structure. And now we are moving on to just putting the electronics on one P of the 2P, and then having the other hub for future payloads and probably the Peltier somewhere in the right side, and having a more compact design in general. So thank you for your time and your attention, and feel free to ask any questions. Thank you. Well, it's just like a cloth, and we will just fold it down to the structure. Yeah, there's reflective. Well, there are like a lot of layers. I don't know exactly what they have. We just bought it. Yeah. It will insulate. We just grab the parameters that the. Huh? Yeah, exactly. Yeah. So the heating up will be done by the electronics, and the electronics will, depending on if they are on, off, and inside and heat flux will make it oscillate a bit, but yeah, it will be quite constant, yeah. Yes?
Why did you choose to use that antenna instead of measuring tape, for example?
Sorry, what kind of?
Why did you choose to use that antenna instead of measuring tape?
Oh, because the tape was, so the way that if you use tape, we had to like make it go around the satellite several times, and we just didn't like the idea because if there's a problem in the so it's very critical, and so if there's any problem during the launch, I don't know, an impact or something, and the unfolding of the antennas doesn't work, you just have a stone in space. So we wanted something that required no input whatsoever, and that could be like folded in a spiral on one of the faces, and another spiral on the other face, and just unfold by itself. Once the sun hits it, it will unfold automatically. Yeah. Any other questions? Well, thank you very much, and I think we'll have lunch now.
Hi, that's the end of the PocketQube section missions for today. We're just going to head over to lunch and back with more talks afterwards. So enjoy.
We're going to stop.